for each color or for each other property, you would choose a new molecule, a new set of atoms in a new constellation. Quantum dots, however, have all the same structure. They have, in fact, the same structure as a bulk material would have. It's the same atoms in the same constellation, just that a small dot has fewer atoms and a bigger dot has larger atoms. The fact that they then change properties is not only their color, it's essentially every property, every material property you can think of, including electric, optical, magnetic, even catalytic effects, how they influence chemical reaction, even the melting point changes. So in this class of material, you have found a way of changing material properties, not by changing the material, but just by the size. And this is a foundational discovery in nanotechnology, the ability to do this in a controlled manner using quantum mechanical effects. The prediction that this would be possible, the prediction that such an effect could occur in theory was made as early as the 1930s. But for the next 5 decades, it seemed near impossible to make such materials because not only do you need perfectly crystalline structures, and you need to control the size exactly, basically atom layer by atom layer, you also need a perfect surface property so that you can get these phenomena and these clear colors. This was not actually expected to be possible. The discovery that this is indeed possible was first made by Alexei Yekimov, who studied colored glasses. And by adding copper and chlorine to a glass, he was able to show first that the copper chloride formed as nanocrystals, so crystals with crystalline properties. He used deep insight into the physical chemistry to control the size exactly, was then able to show that the color of the glass correlated with the size of the particle, and not just in any way the straight line there means, because the straight line is a smoking gun, that this is a quantum effect. So all of this was done in one sweep of results. The discovery was made a second time in a different context by Louis Bruce in the United States, this time for particles in solution, freely in solution, available for further processing. This was done in the context of studying semiconducting particles for their catalytic properties. The vision was, and still is in fact, to use light, such as solar light, to drive chemical reactions. It's a form of solar energy conversion. He looked at relatively small particles and again noticed that the optical properties changed the size. This triggered a lot of interest. Just imagine the ability to suddenly be able to tune material properties not only by making new materials but by their size. Using quantum phenomena is of course very inspiring and triggered a lot of interest to see what could this be used for. But for the next 10 years, this was difficult because the size was not quite well controllable enough, the quality was not quite good enough for real applications. Munjiba Wendi discovered or invented a method for making these particles in a much more controlled manner, the trick being to precisely control the moment in time when nucleation, the beginning of the particle growth, first changes. So he used a hot solvent, well-chosen solvent, and at one instant suddenly injected the reagents, which led to an instantaneous formation of small embryo crystals, a nucleation event. But then the growth stopped because the solution was diluted and the temperature dropped. Then, by reheating and carefully controlling the temperature, again with deep insight in the growth processes, it's possible to control not only the size, but also keep the size in a very narrow window so that only one size gets produced. And the solvent was chosen such that the surface of the particle was protected and gave a very high quality. This opened then for the possibility of applications. And today we see commercial applications, for example, in TV screens, where quantum dots are used